So before we move into the next section, are there any problems that you want me to go over with you from the homework under 19? Let me point out a few of these problems here, ones that we didn't quite get to look at, or these types didn't quite get to look at yesterday. We look at number 7 and 9, for instance. This is working backwards. This is basically saying, okay, here's the sum. Can you figure out the rule that will allow for the sigma notation to produce these terms all spelled out? So the way I like to start these is I like to build out my rule looking at the parts that are not changing, because whatever is not changing is going to have to be in my rule. So I start off building it like this. Well, I see the 1 is not changing. I see the 5 in the denominator is not changing. So I know that this is going to show up for every term. But what is changing is the 1, the 2, the 3, all the way to 11. And typically, we want to start at I equals 1. That's usually the easiest number to start off with. There are some problems that are more difficult and may not start at 1, but we always want to consider, okay, what if we were to start at 1? Am I able to start at 1 and build out and visualize all these terms being showing up? So if I were to start off at I equals 1, then the part that is changing is going to be the variable that needs to be placed. So if I have I in place of the parentheses, then I should be able to get all these terms to show up, because the first term will be 5 times 1, second term will be 5 times 2, 5 times 3, 5 times 4, all the way to 11, and that 11 is going to be my upper bound. For number 9, if you look, this one is starting off, the 7 is not changing, the 6 in the denominator is not changing, the +5 is not changing. What is changing is that numerator. So you know that the numerator is going to be where that variable is. So the I is going to stay in that numerator. So if we let that I be in the numerator, and if we start at 1 and end at 6, we should be able to kind of plug in and see ourselves getting all these terms all the way up until that last term. Number 11 looks a little bit more challenging, because it just all of a sudden goes from 2 all the way to 2n, and so we have to kind of imagine, wait, maybe there's something here that we're not recognizing. Maybe this is they're hiding an I here, because if I were to plug 1, I'm going to get that. If I were to plug 2, I'll get something else. If I were to plug n, I'll get that nth term. So, but it looks like everything is staying the same, and the denominator is staying the same. The 2 over n is staying the same. So this is how I would start it off. I would just copy down all the parts that are not changing. The 2 and the 2n, I want to leave that alone. That part is changing. But I see the n is not changing, and that outside parentheses 2 over n is not changing either. So if I were to start at I equals 1, I'll get 2, but then that I is going to increment it, that is kind of hidden from us. But the next one will be 2 times 2, then 2 times 3, all the way to 2 times n. So I need to let this be 2i in order for us to increment from 2 all the way to 2 times n. So if I were to plug 1 in for that, I'll get the first term. If I were to plug 2, it'll get one of the ... terms here that's hidden from us. If I plug 3, plug 4, plug 5, all the way up to my nth term. If I were to plug in my nth term in for I should be able to safely get that third term. Oops, sorry, I'm missing that cube there. And then 13 through 17, we're just splitting up each of our terms and then relying on our summation rules to substitute all the n's or to create all the n expressions and then plug in the upper bound to get our sum. Any questions 1 through 19? All right, so today's notes, let's go to page 3. So we talked about yesterday how the inverse procedure of slope is area. And what we're doing is we're going to be using area to find our antiderivative. But the easiest area formula that we know are rectangles and squares. So we're going to start off building or approximating the area under a curve using rectangles. But we can draw the rectangles a certain number of ways. So I want to show you what are the ways that we can draw rectangles. So we call these Riemann sums. These are rectangles used to estimate the area of a region. And the important thing is to understand that it's just an estimation. Okay. These are going to be curved regions, and rectangles can only do so much in terms of representing the area of that region. There's always going to be portions that's going to stick out, and our graph, our shaded region is not going to be able to be represented by rectangles unless we have infinite numbers of rectangles, which we will talk about tomorrow. But here we're only going to be doing like maybe 3 to 5 rectangles. So the accuracy is going to be limited. So consider the function f of x equals x squared plus 1. This is a parabola that has a y-intercept at 1. Suppose we want to estimate the area of the shaded region using a given number of rectangles. So one way to do this is if we were to do upper rectangles or circumscribed rectangles. This is where we're going to attach one of the corners of the rectangle to the curve, but we're going to purposely make every rectangle have every rectangle have a portion that sticks above the curve so that we can over-represent or overestimate the region of our area. So here, if let's say I have region 1, region 2, region 3, and region 4. Now for region 1, I would purposely choose the left upper corner because the upper left corner is going to be the higher of the 2 points, and then I'm going to let that represent the height. I'll drag that height over and let that be the area of my first rectangle. For my second rectangle, between this point and this point, I see the left endpoint is higher than my right endpoint. So I'm going to take that left endpoint, sorry, and drag that height over and let that be the height of my second rectangle. For my third rectangle, I'm just choosing between either 0 or 1. 1 is obviously the higher of the 2 points, so I'm going to let that attach to the point on the graph, and I'm going to drag that over, make that rectangle come from the right endpoint. And then for my fourth rectangle, between this point and this point, I want to always choose the higher corner and let that drag over to represent the height. So if I were to find the areas of these 4 rectangles, I'm guaranteed to get a number that is more than the shaded region below the curve. Okay. Likewise, if I were to choose the lower of the 2 endpoints and attach it to the curve, then I can guarantee that every rectangle I draw is going to be inscribed. If it's inscribed, I can guarantee that whatever the area of these rectangles are, it's going to be smaller than the actual area of my shaded region. A third way and fourth way of drawing these rectangles is where we don't really care whether it's an over or under approximation. We're just going to do something consistent all the way through. A left-handed rectangle would be every subinterval, I'm always choosing the left endpoint to attach to the curve, and then let that guide the height of each rectangle. So if you look at all these rectangles here, some rectangles are above, some rectangles are below, but the consistent thing is that every rectangle has a left endpoint that is clearly attached to the height of the curve. And then the right-handed rectangle is where I'm purposely choosing the right endpoint of each subinterval to represent the height of that rectangle in that region. Okay, so on the next page, we're just going to be drawing these rectangles and then finding the areas of these rectangles and adding them up and calling it an approximation. Okay. We don't have to ever worry about how accurate our approximation is. We just have to be able to find the types of approximations that the problem is asking for us to find. Okay. Okay, next page. Use 4 rectangles to estimate the upper and lower sums for the area bounded by x equals 0, y equals 0, x equals 2, and y equals x squared plus 1. So y equals x squared plus 1 is a parabola that you see here, and we're only talking about this shaded region in the first quadrant. So the first thing that we want to do is we want to be able to find the width of each rectangle. We want every rectangle to have the same width, and we're going from 0 to 2. So we're going to take our left endpoint and our right endpoint, subtract it, and divide it by the number of rectangles that we want. We want 4 rectangles, so that's our n value. So our a value, give me a second here. So my width formula is b minus a over n. My a value is 0. My b value is 2. So it's 2 minus 0 over n. I want 4 subintervals. So 2 minus 0 over 4 is equal to 1/2. So I'm going to start at 0. I'm going to keep adding 1/2 until I reach my endpoint. So 0 plus 1/2 is 1/2. Plus 1/2 is 1. Plus 1/2 is 3/2. And then plus 1/2 will give us 2. So I want to find, let's say I want to find my upper sum first. So upper sum, I'm going to represent using uppercase S sub 4. Now, the graph is rising, right? And so between each subinterval, I want to choose the endpoint with the higher y value. So between 0 and 1/2, we know 1/2 is higher than 0. So you're going to highlight that point and drag that over, and we're going to let that be the height of my first rectangle. The graph is always rising, so looks like the right endpoint is always going to be the higher of the two. So for my second region, I'm going to highlight that second point and let that be the height of my second rectangle. Third rectangle, my height is going to be at 3/2, or whatever the y value is at 3/2. And then the fourth rectangle, whatever the y value is at 2. So here's my function. My function is f of x is equal to x squared plus 1. And I'm just going to represent the areas of each of these 4 rectangles. What's the area formula for a rectangle? Length times width, right? What is the width of each of these rectangles? That's the width. Every rectangle has a width of what? 1/2, okay? So width times height, so 1/2 times the height. The height is whatever this height is, right? I'm gonna represent using function notation first, and then we can plug in and find the y value. So if I were to plug 1/2 into the function, that represents my height. So I'll say 1/2 times f of 1/2. This is the area of my first rectangle. Okay. We're going to eventually plug 1/2 into the function and find out what that actual y value is. But I do want us to be comfortable looking at that and knowing what that represents. That represents the height of my rectangle in function notation. Plus, what do you think the area for my second rectangle can be represented as? 1/2 times what? F of 1, yeah. And we just go down the line, right? 1/2 times f of 3/2 plus 1/2 times f of 2. Now, notice that we used every one of these y values, every one of these x values except 0, right? We don't use 0 because 0 doesn't represent the height of any of the upper rectangles that we're looking at. So then we plug 1/2 into the function, 1/2 squared plus 1, whatever that y value is the height of my first rectangle. And then if I were to plug this in the calculator, 1/2 times 1/4 plus 1 will give me 0.625. If I were to plug 1 into the x, I'll get 1 plus 1 is 2. 2 times 1/2 is going to be 1. And all this is calculator work, right? 1/2 times, if I plug 3/2 in for x, I'll get 3/2 squared plus 1, whatever that value is, times 1/2 will be 1.625. And then the last rectangle has an area of 2.5. If I were to add all that up, that will give me 5.75. What do you know about this area approximation in relation to the actual area? This is guaranteed to be what? More, right? Higher, greater than the actual area. We don't know how much greater, but that doesn't matter for us as long as we know what it represents. It represents some over approximation of the area. The accuracy can only do so much because we're using 4 rectangles. Obviously, if we had more rectangles, we can get more accurate approximation, but we're only asked to do 4 rectangles here. So now let's try to find a lower sum of the same region. So lower sum is where we're now going to choose the lower of the 2 heights, corners, to attach to the curve. And you can imagine, instead of starting at 1/2, we're now going to start at 0. So my rectangle is still going to be a width of 1/2. But now between f of 0 and f of 1/2, f of 0 is now the lower of the 2 heights. And we'll let f of 0 represent the inscribed rectangle, the height of my first inscribed rectangle. And then the second rectangle will be width of 1/2, height of f of 1/2. Third rectangle, I'm going to use f of 1 to attach to represent the height of my third rectangle. And the last rectangle, f of 3/2. And if I were to plug this in the calculator, add all that up, this is guaranteed to be what compared to 5.75? More or less? It's got to be less, right? So this is my lower approximation of the shaded region. This is my over approximation of the shaded region. So we know that our actual area will be somewhere between 3.75 and 5.75. We can't, it's not as clean as saying, oh, this is the average of these two numbers. Now, the average of these two numbers will probably be a better approximation, but we can't assume that is going to be the exact area. All we know based off of our limited data is that our actual area is going to be somewhere between a lower sum and upper sum. Okay, next page. Another way to represent the area of a shaded region is what we use middle or midpoint rectangles. This is where we purposely choose the midpoint of each subinterval and let that hit the graph wherever it hits, and let that represent the height of my rectangle. So example 2, estimate the area under the curve y equals 8 over x squared plus 1 from 2 to 6. Use midpoint rule with 4 subintervals. So my a value is 2, my b value is 6, and my n is 4, because I'm still using 4 rectangles here. So if I do b minus a over n, 6 minus 2 over 4, that will give me a width of 1. So I can step through and start at 2 and keep adding 1 to get to the next endpoint. So every rectangle has a width of 1, but instead of using f of 1, or sorry, f of 2 or f of 3 to attach itself as the height of the rectangle, we're going to purposely choose the midpoint to attach. And if you can imagine, the midpoint will create a better approximation because you have some portions of the rectangle that's going to stick above the curve, some rectangles, some regions that stick below the curve. And so that should give us a better approximation than if the entire rectangle is either above or below the curve. So what's between 2 and 3? What's the midpoint between 2 and 3? 2.5, right? So we can let 2.5 attach to the curve and let that represent the height of my first rectangle. So M of 4, I'm going to use 4 rectangles to approximate my middle rectangles. So my width is 1 for my first rectangle. My first rectangle, it will have a height that can be represented as f of 2.5. Whatever this height is. And the second rectangle also has a width of 1, but it's going to be f of 3.5 because we're purposely choosing the midpoint of the subinterval to attach to the curve and let that represent the height of that rectangle. Next rectangle, width of 1, height of f of 4.5. And then last rectangle, width of 1, height of f of 5.5. So then we're going to get 1.103. If I were to plug 2.5 into the function 8 over x squared plus 1, that will give me 1.103. And I'm just going to go down the line and show the decimal values for each of these areas. So my midpoint sum, or my midpoint approximation, is going to be 2.34. We don't know if this is an under approximation or over approximation, but we do know that this is a better approximation than just a left-handed rectangle or right-handed rectangle. Okay, let's do some of these problems together. Page 7. Sorry, it's a little bit grainy here, but the interval that we're looking at is between 0 and 4 for both of these. This is 31. These are both 31s, but I just copied it twice onto the paper. We can do 1 for lower sum and 1 for upper sum. So let's start off with upper sum. And the shaded region is between 0 and 4. It's not very clear, but that's the shaded region. So we're going to purposely draw 4 rectangles and let every rectangle have portions that stick above the shaded region. So if you want to first highlight the shaded region, we're trying to approximate the region beneath the curve between x values of 0 and 4. So upper sum, that means we're purposely choosing whichever interval, endpoint interval, has the higher two y value. So between 0 and 1, which has a higher y value on the curve? 1, right? So you're going to highlight 1, and you're going to drag that point over, and you're going to draw a rectangle. That first rectangle will be clearly sticking above the curve. Okay. For my second interval, between 1 and 2, which one has the higher y value? 2. So highlight that point, drag that height over. Okay. What about the third rectangle? Between 2 and 3, which one has a higher y value? 3, right? So it looks like it's sitting at a midpoint there. And then between 3 and 4, which one is higher y value? 4, right? So highlight that point, drag over. So now our goal is we just want to find the area of each rectangle. So we're going to call this uppercase S of 4 because we're using 4 rectangles. What is the width of my first rectangle? 1. What is the height of my first rectangle? 3. Okay, so 1 times 3. Second rectangle, also a width of 1 and a height of what? 4. Third rectangle, also a width of 1. What does the height look like to you? Yeah, I mean, it's our approximation, right? We don't really know exactly what it is, but we know somewhere between 4 and 5. So our best guess is 4.5. But if you choose other decimals, you can make an argument for that as well. And then the last area is 1 times what's the height of my last rectangle? 5. Good. And if I were to add that up, I would get 16.5, and I know that 16.5 is going to be more than the actual area of that shaded region. – 31 part B, let's do a lower sum. Again, you can, if you want to highlight that shaded region to see what we're trying to approximate. But now we want every rectangle to clearly be beneath the curve. So between 0 and 1, which one has the lower y value? 1, right? So, sorry, 0, right? So 0, highlight that point, drag that over. That's going to be the height of the rectangle, my first rectangle. Second rectangle, if I'm choosing between 1 and 2, which one has a lower y value? At 1, right? So I'm going to see where that hits the graph. Hits the graph at 3. So at 3, you're going to drag that height over. But clearly, every rectangle that we're drawing is sitting beneath the curve. Next up, between 2 and 3, 2 has the f of 2 has a lower y value than f of 3. So drag that over. And then between 3 and 4, 3 has a lower y value. So now we're going to find the areas of each of those 4 rectangles, add that together, and that should give us a lower sum, a lower area than this approximation. Okay? We don't know what the actual area is, but we do know that it's going to be somewhere between 12.5 and 16.5. Okay, any questions so far? I want to do 33, the rest of this page here with you, but I want to change the directions a little bit. I want to say left-handed rectangle for part A and right-handed rectangle for part B. So, so now so now we don't care if it's an upper or lower sum. We just want to always choose the left-handed rectangle. And that's going to be more of what we need to be able to do on the AP exam. On the AP exam, you're not going to see much upper rectangle or lower rectangle. Most of the problems will be asking, can you create a left-handed rectangle or a right-handed rectangle? So let's look at 33. Okay, the interval is going to be from 0 to 1. And we want to use 4 rectangles. So part A, we're going to do left-handed rectangles. So the first thing is, let's create the width, right? The width you can find using your A, your B value, and your N. So your width is going to be B minus A over N. So 1 minus 0 over 4. What's my width going to be? Just 1/4, right? So now I'm going to take my interval and I'm going to keep adding 1/4 until I reach my right endpoint. So I'll start at 0. Next up, 1/4. Next up, 2/4 or 1/2. Next up, 3/4. And next up, 4/4 or 1. My graph looks something like this. If I want to do left-handed rectangle, then I'm going to be choosing the left endpoint to be my height. It also happens to be an inscribed rectangle, but we're going to make this left-handed rectangles. So if I want to find my area approximation, my width is 1/4. And then my heights, I want to attach 0 into the function. So I'm going to say y of 0. I'm going to find the areas or the heights later. I just want us to practice using function notation first before we plug it in. Second rectangle, width is still 1/4. And then I need to attach 1/4 to the curve to get to that point, because I want that point to represent the height of my second rectangle. So y of 1/4. Third rectangle would be f of 2/4 or f of 1/2 or y of 1/2. And then last rectangle, I want to attach 3/4 to the function, so y of 3/4. And if I were to plug this in the calculator, I'll get 1/4 times 0, which is 0. The square root of 1/4 is 1/2. 1/2 times 1/4 is 1/8. I'm going to add all these up, right? Plugging them into the function one by one. And it's going to end up giving us 0.518. It's just an approximation. Okay, part B, let's see if we can do a right-handed rectangle. We may not even have to redraw everything. We can use a lot of the data. But then instead of starting at 0, we're going to start at 1/4. If it helps, I can redraw it for you. So now I'm just purposely choosing the right endpoint to represent the heights. It also happens to be circumscribed, but so width is all going to be 1/4. But now I want to attach 1/4 into the function to get the height, to represent the height of my first rectangle, because I want to purposely choose the right endpoint of each subinterval. Let me do 35 part A with you, and then I want to do 25 with you so you kind of see what these problems look like. But for 35A, let's again do left-handed rectangles. And then for 35B, we can do right-handed rectangle. So we're going from 1 to 2. And here, 1, 2, 3, 4, 5. Looks like we're doing 5 rectangles there. So we start off by building the width. B minus A over N, which is 1/5. So starting at 1, we're going to keep adding 1/5 until we reach our destination, which is 2. So 1 is something is 5/5. 5/5 plus 1/5 is 6/5. Then 7/5. Then 8/5. Then 9/5. Then 10/5, which is 2. We want to do a left-handed rectangle. Well, the graph looks something like this. Then we want to attach the the left corner to each subinterval to the curve. So my area, every width is 1/5. And then it's going to be y of 1 plus, and then 1/5 y of 6/5 plus, and let's go all the way to 9/5, right? We don't use 2 because 2 doesn't represent the left endpoint of any subinterval. And it's just a matter of setting it up and plugging into your calculator. Yeah, and you'll do the same thing for 25, 27, and 29. Find your width and build out your width and area, your width and height for each of the subinterval. So you can do all your homework directly in your packet. So in this case, I did print everything out. So tomorrow I'll just be checking pages 7 and 8 for your homework. Pages 7 and 8 for your homework. We did a bunch of it already, so you should have to finish off what we haven't done yet. All right, come get your phones. I'll send a reminder this afternoon.